Okay, recording has started. So this week we will learn about evaluating properties of substances. When we say evaluating of properties, it's related to determining the relationship between pressure, temperature, specific volume, enthalpy, internal energy, and entropy. So they are related to each other depending on the phase of the matter. For the case of uh, air, for instance, as you remember, according to the ideal gas law, the pressure, the density, and the temperature of the air are related to each other. So in order to set or in order to fix a state, it's necessary to know two of the properties. Remember that according to the ideal gas law, PV is equal to MRT. So if you divide each side by volume, you get pressure being equal to density times R times temperature. Here, density is in kilograms per cubical meter. R is the ideal gas law, ideal gas constant for the specific gas, whichever the gas is, and T is the temperature in Kelvin. So as you can see, pressure is related directly to density and temperature. However, during the phase change means that changing the phase of a substance from solid to liquid or liquid to gas, there are only two properties that are related to each other. So at a given pressure during the phase change, if you know the pressure, you know the temperature, or vice versa. These temperatures or pressures during the phase change are called saturation temperatures or saturation pressures. For instance, at atmospheric pressure, the saturation temperature of water is 100 Celsius because it starts to change phase at 100 Celsius if the pressure is atmospheric. So in this case, as you can see, one property is dependent upon only on a second one. However, outside the saturation, we need to have two different properties, two intensive properties to get the third property, as in the case of air as an ideal gas. So as a result, we can say that except for the situation where there is a phase change, one property is related to two other properties. For instance, pressure is related to temperature and specific volume, or internal energy is related to temperature and specific volume, and so forth. By the way, the specific volume is the inverse of the density. So specific volume is 1 over rho. Rho, as you know, is the mass of a substance per unit volume, and specific volume is the volume of a substance per unit mass. So they are inverse of each other. Sometimes you can see it as specific volume, sometimes 1 over density. They are just inverse of each other. So we use PVT relationships to determine the relation between pressure, temperature, volume, or other properties of a material, of a substance. PVT surface is a three-dimensional graph This is a three-dimensional graph. X-axis is specific volume, y-axis is temperature, and z-axis is pressure. And this three-dimensional graph gives you the relationship between pressure, specific volume, and temperature. This specific volume can be replaced by, for instance, internal energy or enthalpy, or, for instance, entropy. However, working with three-dimensional graphs are not so easy. So instead of using three-dimensional graphs, we usually use the two-dimensional graphs, which are actually the projection of three-dimensional graph on one surface or on one plane. You have taken technical drawing, you know how to make projections on planes. So if you take the projection of this three-dimensional graph onto this plane, for instance, the projection of it is going to be like something like that. Or if you take the projection of this three-dimensional graph at the bottom plane, it's going to be something like this. So these are more practical than using all the three-dimensional graphs. So when you take the projection of the curve here, the graph here, for instance, on PT plane, so this is the PT plane, so PT plane is the back plane, you get a phase diagram which has solid liquid phase change line, solid vapor phase change line, and liquid vapor phase change line. The intersection of three phase change line is called triple point. At the triple point, all three phases are in equilibrium. So as you can see, at the triple point, you have liquid, vapor, and solid existing at the same time. But for instance, for water, this is a very low pressure as well as a very low temperature. The triple point of water is about 0 Celsius and a pressure which is very close to zero. Not zero, of course, but very close to zero. On the other hand, for instance, for carbon dioxide, the triple point is much higher, like 5 atmospheres. So if you remove the pressure on carbon dioxide, it becomes vapor directly from solid. If the temperature is low enough, the solid carbon dioxide becomes a vapor carbon dioxide because the pressure is below the triple point, and this phenomenon is called sublimation. So if temperature and pressure is low enough, the carbon dioxide changes phase from solid to vapor directly without passing through liquid, and this phenomenon is called sublimation. The second graph is the projection of the three-dimensional graph on PV plane. So when you project the three-dimensional graph on the PV plane, you see that the temperature curves are projected on the plane like this, and you have the triple line instead of a triple point here, extending like this. The left side of the triple line, if the pressure is low, is solid. The bottom part of the triple line is solid plus vapor. Over the curve, which is called a saturation curve, we have always a condition which is saturation. Inside the curve, we have a mixture of liquid and vapor. The right-hand side of the curve is vapor, but vapor at a high temperature, which we call superheated vapor. The left-hand side of the graph, if the specific volume is high enough, is liquid, and it's most of the time called as subcooled liquid or compressed liquid. The top point of the curve is called critical point. Above the critical point, there is no distinction between vapor phase or liquid phase. So the term vapor or liquid loses its meaning above the critical point. So triple line is a line below which the sublimation can occur. The saturation is the phenomenon at which a substance changes from solid to liquid or liquid to gas. Inside the dome, inside the curve, we have a mixture of liquid and vapor. The left-hand side of the curve is called saturated liquid. The right-hand side of the curve is called saturated vapor. The outside of the curve, the right-hand side outside of the curve is called superheated vapor. The outside of the left-hand side of the curve is called subcooled liquid or compressed liquid. So this is most of the time we will be using for evaluating the properties of substances. And this curve is actually the TV curve. So TV diagram is what we are going to use most of the time. Sometimes we may be using PV diagram also. Let's take a look at the TV diagram. So on the TV diagram, you see the saturation line first. So the saturation line gives you the pressures and temperatures at which phase change occurs. So you see different pressures. For instance, there is one pressure here, which is atmospheric pressure, 101 bar. This is atmospheric pressure. At atmospheric pressure, if this is water, you can see that the phase change occurs at 100 Celsius. If this is for water, in 1 atmosphere, the phase change takes place at 1 atmosphere. And it starts with saturated liquid. And during the phase change, temperature is constant. And it ends up with saturated vapor. Inside the curve, we have a mixture of liquid and gas, liquid and vapor, depending on the location inside the mixture zone. If we have a higher pressure, for instance, if the pressure is 10 megapascals instead of 0.1 megapascal here, then you see that the phase change takes place at a much higher temperature. It could be something around 200. Or if you increase the pressure even further, then you get the critical point. The critical point for water is 22 megapascals, which is a very high pressure. At this location, as you can see, there is no distinct phase change from liquid to gas. So above the critical point, we have a critical substance, which we cannot call either liquid or gas. So it's a critical substance. So to repeat, we have liquid at the left hand side, on the curve we have saturated liquid. Inside the curve we have mixture. On the right hand side we have saturated vapor, and outside the curve we have superheated vapor. As you can see, in the saturation zone or inside the mixture zone, you only need either temperature or pressure. So you need only one of them. But outside the saturation curve, if you are given a superheated vapor, for instance, you not only need the temperature but also the pressure to fix the state. So except for the saturation, you always need two intensive properties to fix a state, such as this one or that one. But inside the saturation curve or on the saturation curve, you either need the temperature or the pressure. Similarly, a PV diagram would have P, the pressure on the y-axis, V on the x-axis. The curve is very similar to this. However, the temperature curves do not look like the pressure curves. Instead, the temperature curves are like this. So in the case of pressure versus volume, the temperature curves are given as shown here. So let's take a look at what happens actually during the phase change. Suppose that there is liquid water below the saturation temperature at a given pressure. Let's suppose that the outside pressure is atmospheric pressure. So at the outside we have atmospheric pressure, so that because the piston is in equilibrium, inside pressure must also be atmospheric, because the piston is in equilibrium. So the bottom force is P times area. The top force is also P times area, which means it's statically in equilibrium. Some of the forces are zero. So if the outside pressure is atmospheric, of course we are neglecting the weight of the piston. We assume that the piston does not have any weight. In this case, the top force and the bottom force must be equal, meaning that the pressure outside must be equal to pressure inside. So we have liquid water at a temperature below the saturation temperature first. So it means that, for instance, we are here. So at the point 1, the water has a temperature of 20, and the pressure is atmospheric pressure. As we heat it up, suppose that we provide heat to this cylinder. Because of the heat interaction between the cylinder and the heat source, the temperature of the water will increase. So when the temperature comes to 100 Celsius, because in 1 atmosphere pressure, the saturation temperature or the phase change temperature for water is 100 Celsius, it starts to change its phase. So it starts to change its phase. You can see the phenomenon of phase change. So suppose that this one represents a situation somewhere here. So part of it is liquid, part of it vapor. So it's a mixture of vapor and liquid during the phase change. So there is a mixture of water and vapor. If you further heat this system so that the whole liquid becomes vapor, then you come to this point, which is a saturated vapor. So you have a situation in which the liquid water, which was initially, let's say, at 20 Celsius, it was heated up to saturation temperature, then it has started to change phase, as in this uh, figure B. Then, when all the liquid has changed phase to vapor, then you have saturated vapor. It started with liquid, subcooled liquid, because it's called subcooled due to the fact that its temperature is lower than the saturation temperature. When the temperature becomes the saturation temperature, which is 100 Celsius for 1 atmosphere for water, phase change starts. During the phase change, the liquid water is converted to vapor, gas water. So when all the liquid is converted to vapor, it's called saturated liquid, saturated vapor. So you have at this point saturated vapor. At this point, saturated liquid. Inside you have mixture, outside you have subcooled or compressed liquid. It's called subcooled or compressed because its temperature is lower than the saturation temperature. So what can we do outside the saturation curve? If it's compressed liquid, then we can use compressed liquid tables, or most of the time, the property in a compressed liquid is very close to the property at the liquid at the saturation. So for the time being, let's move to the mixture zone. So we would like to find out the properties at the mixture zone. At the mixture zone, we need to provide a definition of quality of vapor or quality of steam. Quality of vapor is the mass of the vapor divided by the total mass of the mixture of the vapor and liquid. So it gives you the percentage of the vapor as mass within the mixture. So if the quality is 0, it means that it's completely 0, it's completely liquid. So it's saturated liquid. If on the other hand, it's converted wholly as vapor, then quality is 1. So it occurs at the point of saturated vapor. In between, you can have a quality between 0 and 1. So this is what the situation is for a mixture. So inside the mixture zone, you have a quality of steam, which is so inside the mixture zone, you have a quality of steam, which is between 0 and 1. It's 0 on the saturated liquid, and it's 1 at the saturated vapor point. So once you get the value for the quality of the steam, then you can calculate the property easily, because the property in the mixture is directly related to the quality of the steam. In this curve, in this figure, you see a TV diagram for water. So as you can see, you have the saturation curve, which is called dome. Sometimes it's called dome, saturation dome. Inside the saturation dome, we have mixture of liquid and vapor. The left-hand side of the saturation dome is liquid, or sometimes it's called subcooled liquid or compressed liquid. The right-hand side of the saturation dome is called vapor, or sometimes, most of the time, it's called superheated vapor. The saturation curve itself, the left-hand side is saturated liquid, and the right-hand side is saturated vapor, and the top point is called critical point. And these are different pressure values. For instance, this is the pressure for atmospheric pressure. This one is a higher pressure, like 10 atmosphere. This one is the critical pressure, which passes through the critical point, is 22 megapascals. And you can have supercritical pressures, which are pressures over the critical pressure. For instance, 30 megapascal passes through completely outside the saturation curve. So how can we find out the properties in the saturation case? Because during the saturation, you only need one of the properties, one of the intensive properties as pressure or temperature. So you have two types of saturation tables. One table is given for temperature, so it starts with temperature. Another type of table can be pressure table. So for the case of pressure table, the table starts with pressure. But both tables have pressures and temperatures. The pressures and temperatures are actually the saturation values. For instance, for the case of temperature, if you go to 100 Celsius, you will find that the pressure is 1.014 bars, which is atmospheric pressure. So saturation temperature versus saturation pressure. Or for the pressure table, if you go to the pressure of 1 bar is a little bit different from atmospheric, but very close to atmospheric pressure, you get a saturation temperature of almost 100. So depending on what you are given, you can use either pressure table or temperature table. Suppose that you are given a temperature. So by using the temperature table, you can obtain all the properties regarding to this temperature. For instance, if the temperature is, let's say, 14 Celsius, the corresponding saturation pressure is this much. In the first two columns, you get the specific volume of liquid and gas. So the first one belongs to liquid, and the second one belongs to vapor. So what it means is, remember that we have the PV curve like this. Sorry. TV curve like this. So if you are using 14 Celsius, let's say this is 14 Celsius, the first value here is provided with Vf, and when it becomes a saturated vapor, the second value is given as V gas. So the first one is Vf, the second one is V gas. But be careful that Vf is a very small value, so it's multiplied by 1000. So what you see here is 1000 times the specific volume of water. And the second one belongs to the specific volume of the gas. So similarly, the second pair of the graph table is given for internal energy. The first one is the internal energy at this temperature of the liquid. The second one is the internal energy of the gas at this temperature again. The third group of columns is enthalpy. Enthalpy has three different columns. The first column is the enthalpy of the liquid. The third one is the enthalpy of the gas. And in between, you can find the difference between the enthalpy of the gas and the liquid. So the middle column is actually, it's called HFG. The difference between the third column minus the first column. So actually it's not necessary to have this column, but for the sake of practical reasons, it may be provided to you. So HFG is actually the difference of the enthalpy of the gas and the enthalpy of the liquid. And the final two columns belong to entropy, which we haven't learned yet. And similarly, the first one belongs to entropy of the liquid, saturated liquid, and the next one belongs to the entropy of the saturated vapor. So the table starts from a triple point temperature, almost zero, and goes up to temperatures up to the critical temperature, which is 373. A second type table is, as I said, the pressure table. In the pressure table, instead of starting with a pressure temperature, you can start with a pressure. For instance, if you are given a pressure of, let's say, 4 bars, so the corresponding saturation temperature is 141. It means that water starts changing phase at 143 Celsius if the pressure is 4 bars. The corresponding liquid and saturated vapor specific volumes are given. The enthalpies: saturated liquid, saturated vapor, and in between you have the difference of the vapor and gas. Internal energy, sorry, this is not correct, so let me, oops, all right. So these are the internal energies given for this saturation pressure of 4 bar, and the corresponding saturation temperatures is 143 Celsius. And the next three columns belong to enthalpies. The first one is the enthalpy of the saturated liquid. The last one is the enthalpy of the saturated vapor. And in between, you have the difference of saturated vapor and saturated liquid. And finally, we have the last two columns belonging to entropy, again, saturated liquid and saturated vapor. So as I said, the situation with the saturation is relatively easy because you either need to have the pressure or temperature to read out the values, the properties. On the other hand, for the case of superheat, you have to have two different properties. So in order to use the tables for superheat region, you have to have both the temperature and pressure. So in order to find, for instance, the properties of the vapor or the steam at 10 bars and so many degrees, we don't know, let's say 200 degrees, you need to have both pressure and temperature at the same time so that you can find the specific volume, the internal energy, the enthalpy, and entropy. So this is how you use the superheat table. The superheat table starts with first pressure. So as you can see, at the top of the tables, you are always given pressures, increasing pressures. And the table continues like this, continues on the second page. This is not the complete table. I have provided the tables as an attachment to the course resources, so you can see them in All Learn as attachments. So once you have the pressure, for instance, you are given a pressure of 3 bars, let's say in the superheat region, you have a pressure of 3 bars. So you need to use this one, 3 bars. So you need to use this one. And also, let's say that the temperature is 240. So the temperature is 240. You need to read all these values as table values. So the first value is specific volume, the second value is internal energy, the third value is enthalpy, and the last value is entropy. So by using two intensive properties as pressure and temperature, you can read out necessary properties as specific volume, internal energy, enthalpy, and entropy. Of course, the tables do not give you exact values all the time. Sometimes you may need to find an intermediate value. So what is an intermediate value? When you take a look at the table, you may see a situation where the table has, for instance, 200 and 240, but you are interested in finding the value for 215. So you need to find the value which is in between the table values of 200 and 240. The value for 200 is given as 0.206. The table value for 240 is given as 0.2275, but you need to find the value for 215. The process of finding the intermediate value is called interpolation. Interpolation is finding an intermediate value. Our assumption is the values between 200 and 240 varies linearly. So we have a linear variation between 200 Celsius and 240 Celsius, 200 and 240 Celsius, and the corresponding values are 0.206 and the other value is this one. But you are interested in finding the value for 215. As you can see, because the variation is linear, you can write the equations of the line, because the line has an equation of y is equal to mx plus n. This is the equation of this line. You can obtain the equation of this line by using the given values. Then you can use this equation of the line for any value inside the given values. Or you can use the principle of similar triangles. You have two triangles which are similar to each other. One triangle is the outer triangle. The second triangle is the smaller triangle. So according to similar triangles, you can write this divided by that, which is equal to this part divided by that part. Again, you only need to find out the value in between here. And in order to find out, your assumption is the variation of the values are linear. So by using the linear equation, linear variation, you can either obtain the equation of the line. So it means that first you need to find the slope of the line, then get the value for n by using the four given values. Then once you have the equation of the line, you can use it for any point in between, or you can just write down the similar triangle equation in which this height divided by that height is equal to this distance divided by that distance. As you can see, there is no one single way to do it. You can use whatever is more practical for you, but at the end, your objective is to find out the value which falls in between the lower value in the table and higher value in the table. So according to the calculation, the value for the 215 is calculated to be 0.2141, which is between this and that. So as you can see, it's obtained from the linear change of the values. This is called interpolation or linear interpolation. So once you have the values of the saturation, you can use it to calculate the properties in the mixing zone. Because in the mixing zone, you have a mixture of liquid and vapor, and the definition of this mixture is given by the quality. The quality is mass of the vapor divided by the total mass. So once you have the quality, you can use it for calculating the properties in mixture. So if you have the quality of the vapor, then for any property, let's say this any property is y, y can be v or u or H or S. So it's a generic property. It's calculated from Y of the fluid plus sorry. It's better to do it right like this. I'm going to use the same form so it doesn't look differently. Y of the fluid plus the quality of the steam, times the difference between the Y of the gas minus Y of the fluid. So this gives you the property of the mixture in the mixture zone. As I said, it can be, this Y can represent the specific volume, it can be the internal energy, it can be the enthalpy or entropy. You always use the same kind of formulation to find the property in the mixture zone. Okay, there is a example, numerical example regarding this. So before moving on to this, let me ask you if you have any questions. The concepts here are not so difficult, but you need to understand the differentiation between the saturation liquid, the mixture, the saturated vapor, subcooled vapor, and superheat vapor. And you have to be sure that you need to use the saturation tables if you are given uh, the saturation temperature or saturation pressure, but you have to use both pressure and temperature if you are given a situation which is superheat vapor. So in the case of a superheat vapor, you have to use both temperature and pressure, or two intensity properties, let's say. Okay, if you don't have any question, we can have a break of 10 minutes. So we will continue at 2 o'clock, 2 p.m. because it has started. In this numerical example, a water vapor mixture is placed inside this closed container. The pressure inside the container is atmospheric. There is 1 atmosphere pressure inside this container, and it has a mixture of water and vapor. And it says that the quality of the mixture is 0.5. So what it means that X equal 0.5, meaning that 50% of the mass inside is vapor and the remaining 50% is liquid. So from the 1 atmosphere pressure, initial pressure, it started to be heated. As it's heated, because the volume is constant, it cannot expand. Because it cannot expand, the pressure must increase. So you can see that initially pressure was 1 atmosphere, 1 bar. When it's heated, the pressure becomes 1.5 bar. Then it's further heated until it becomes a saturated vapor. So at this point, you can see that all the water has converted to vapor, whereas at the state 2, even though the quality has increased, we get a quality greater than 0.5 here because you can see location. So the closer to the saturated vapor, the higher the X. X is 1 here, so X is 0.5 here. It's not linear in any case, but you can determine that the closer to saturated vapor, the higher the X value. So you can also uh, say that the quality in the second state is higher than 0.5, which we will calculate. And at the state 3, it becomes completely vapor, meaning that X is 1 here at this location. So X is 1 here. Here, X is greater than 0.5. And here, X is equal to 0.5. So in the mixture zone, we know that any property can be calculated from the liquid property plus the quality times the difference between gas property and liquid property. We have defined as a general rule, any property in the mixture is equal to property of the liquid plus the quality times the difference between the property of vapor, gas, and the liquid. So because the property here is the specific volume, the specific volume of the mixture is the specific volume of the liquid plus the quality times the difference of the specific volume of the gas and the liquid. Because we have atmospheric pressure and 50% of quality, then we can calculate the specific volume in the mixture as this one is the table value for the saturated vapor saturated liquid specific volume. This 0.5 is the quality. The specific volume for saturated vapor minus the specific volume for saturated liquid. So you can see that the value for the specific volume in the mixture is 0.84, which is between the specific volume of gas and specific volume of liquid. So we can say that the liquid specific volume is less than the mixture specific volume, which is less than the gas specific volume. So it's between the gas and the liquid, which can be seen here. It's between the liquid and gas. So this is the calculated, this one is the calculated specific volume. So as the pressure is increased to 1.5 atmosphere, 1.5 bar, sorry, because the container is rigid, its volume does not change, we have the same specific volume, because specific volume by definition is specific volume is mass divided by volume. Mass is constant, volume is constant for a rigid container, so specific volume is constant. It means that this specific volume must be the same for also the second stage, second phase, second state. So in the second state, we have a higher pressure, but still we have the same specific volume. However, this time, even though we have the same specific volume, we have a higher pressure we need to go to the table again and find the specific volume for liquid and gas, but this time for a pressure of 1.5 bar. So these are the values of the specific volume of water at 1.5 bar. And from that, you can calculate the new quality of the water by using the same specific volume as well as the specific volumes of the liquid and gas obtained from the saturation pressure of 1.5 bars. So, as you can see, the new specific volume is 73%, which is higher than 50%, meaning that more water has converted to gas, so the quality has increased. For the case of state 3, you have saturated vapor, but this saturated vapor has the same specific volume as state 2 and state 1. So you will use the same specific volume here, but you will use it as a specific volume of the saturated vapor because, as you know, in this location it's saturated vapor. Even though you use the same saturated same specific volume, at this point, at this state, it becomes saturated vapor. So you will set the value of this saturated value of the specific volume as saturated vapor specific volume for the state 3. So you need to go to the table and you will find out that this specific volume belongs to the pressure of 2.11 bars. You may need to use interpolation because it may not be possible to see this value directly in the table. For instance, this is 0.84. Let's go to the table. We need to use the saturation table. So we have a saturated vapor liquid specific volume of 0.84. So 0.84 is somewhere here. We have 0.88, 0.71. So it's between this and that. And the corresponding pressures is 2 and 2.5. So by using the interpolation, you can find that the pressure should be between 2 and 2.5. And at the end of the interpolation, the pressure is found to be 2.11. Interpolation is important. You need to use it for several instances, several cases. So you have to make sure that you understand the application of interpolation well. In the second numerical example, this time we are given a refrigerant R134A. This is a refrigerant of R134A. And I have provided you with the tables of refrigerant R134A also. In the beginning, the cylinder piston system has R134A, which was at a phase of saturated vapor. So at the beginning, it was saturated vapor. So it's heated to a temperature of 45 Celsius. Let me put it in SI units because the problem is given in IP units. Initially, the mass of the R134A is 0.045 kilograms. Because it's a closed system, the mass does not change. And initial pressure is 137 kilopascals. It's open to atmosphere, so the total pressure is the pressure of the atmospheric pressure plus the weight of the piston. So if you take a look at the piston and the gas, we have at the bottom P gas, and at the bottom we have P gas and area. So at the bottom we have P gas times area. But at the top we have P atmosphere times area plus the weight of the piston. So what you're going to do is to find the total pressure inside the gas, which is given as 137 kilopascals. Normally, atmospheric pressure is 101 kilopascals, so we have a higher pressure inside the piston than atmospheric pressure. So it's heated to a temperature of 18 Celsius. So it starts with a low temperature, and this low temperature can be found from the saturation table of R134A, because you are given the pressure. So in the pressure table, you can determine the temperature of saturation. So initially it was saturated vapor inside the container, inside the piston cylinder system. As it's heated, the refrigerant becomes superheated. So it becomes superheated, and the superheat temperature is given to you. So initial volume of the piston cylinder system is calculated from mass times specific volume. Here we have saturated vapor, so you can use the saturated vapor specific volume times the mass is given to you. So it gives you the initial volume of the cylinder piston system. Then when it becomes superheated at 18 Celsius and 1.38 bars, it's given to you in the problem statement. It says that the piston cylinder system is heated so that the pressure becomes 1.38 bars and the temperature is 18.3 Celsius. So you need to use the superheat table, because in superheat table you need both the temperature and pressure. From the superheat table you can calculate the new volume or the new specific volume, but in the superheat table you are not given neither directly the pressure nor directly the temperature, because if you look at the tables you will see that you don't have 134, 38 bars. Instead you have 1 bar and 1.4 bar. So it's between, the pressure is between 1 bar and 1.4 bar. The given pressure is 134, 38. So you don't have the exact pressure. Also, you don't have the exact temperature. So instead of 18 Celsius, 18.3 Celsius, you have, 10 and 20. So instead of 18, you have 10 and 20. And instead of 1.38 bars, you have 1 bar and 1.4 bar. It means that you may need to use interpolation twice. So first, you take the pressure to be 1 bar and calculate the specific volume by doing interpolation for 18.3 Celsius. So you repeat this procedure for 1.4 bar and you calculate the specific volume for 18.3 again. Now you have the specific volume for 18.3, but the pressure is still not 1.38 bars. So as a new interpolation, you can use the interpolated value here and interpolated value here to find out the interpolation for a pressure of 1.38 bars. As a summary, I can say that you have to use the interpolation 3 times. So for 10 Celsius, you can use the interpolation, find out the value for pressure. You can do the same for the higher pressure, higher temperature, and you can do another interpolation for intermediate pressure. So keeping the temperature, for instance, constant, here we kept the pressures constant. First we took the pressure of 1 bar, then we took the pressure of 1 bar, then we used interpolation to find the situation for an intermediate pressure. Or you can do it like this as well. You can keep the temperature constant, interpolate between 1 bar and 1.4 bar. Then you take the temperature of 20 and you interpolate the values between 1 bar and 1.38 bar again. So once you have the value, then you can use the interpolation of temperatures. So because you have interpolated the values for intermediate pressure, then you can use this intermediate pressure, interpolated value for intermediate temperature, which is 18.4. So you can do it both ways, either keep the pressures constant, use the interpolation of the temperatures, or keep the temperature constant, use the interpolation of pressures. They will give you the same answers. By the way, it's also asking you the work done during this expansion because the piston is moving up in a closed system. If there is a piston cylinder system, the work done is equal to integral of P times dV. And because in this case P is constant, it's free at the top, so you can see that it's expanding freely. The integral, the pressure goes out of the integral, so that the work during the expansion is just pressure times the volume difference. So 157 joules is the amount of work done during the expansion. It's positive because the system, the gas, is doing work on the surroundings. Otherwise, it would be a negative work. So we have already mentioned that the total energy of a system consists of the summation of internal energy as well as kinetic potential and other kinds of energies. Sometimes it's customary to use the concept of enthalpy because enthalpy is a combination property. It's the total energy of internal energy plus the flow work. The PV is called flow work. So the table gives you enthalpy separately, but if you take a look at the table, you will see that the summation of internal energy from the table plus the pressure and the volume from the table is going to give you the enthalpy. So as a matter of fact, it was not necessary to give you the enthalpy because you could calculate it. But for the sake of practicality, the table provides you with also enthalpy. Enthalpy, as I said, is a combination property, and it's the total energy of a fluid, which is consisted of internal energy plus the flow work. Inside the mixture zone, you can use the general rule to find out the property. Remember, the general rule to find out the property is to use this. So whether it's internal energy or enthalpy or specific volume, you can use the same formula for calculation of any property inside the mixture. So the calculation of the internal energy inside the mixture zone, you see that it's exactly the same as the calculation of specific volume, or you could calculate the enthalpy inside the mixture, and the general formula is always the same. It's always Y is equal to YF plus X times YFG, and YFG is just the difference between the gas and the fluid. Another example, which is also given in IP unit systems, British units. This time, a well-insulated rigid tank, meaning that there is no heat loss or heat gain, of 0.28 cubical meter is filled with water initially of 100 Celsius. It's saturated, so initially it's a saturated water at 100 Celsius, saturated vapor. So initially we have saturated vapor inside this insulated tank in 1 atmosphere pressure. Then the saturated vapor is stirred with a paddle. So by stirring with a paddle, it means that we add energy by work. Remember, work can be transferred into a closed system by either heat or work. So this time, work is added as energy into the system. So by adding this energy as work, it says that its temperature is increased, as we expect, as well as the pressure is increased. Why does the pressure increase? Because it's a closed tank, so it cannot expand. Because it cannot expand, the pressure must increase. The pressure volume graph and temperature volume graph. In the case of pressure volume graph, you can see that the temperature is increasing from the first temperature, 100 Celsius, to a second temperature, or in temperature volume graph, you can see that the pressure is increasing from 1 atmospheric pressure to a higher pressure. It says 20 psi I have the conversion of this pressure, but in any case, what we should understand is at the end of the stirring, the saturated vapor at atmospheric pressure becomes superheated vapor, and we would like to find out the properties at the end of the stirring. We know that the volume is the same, so the specific volume must be the same. So the specific volume at state 1 must be the same as specific volume at state 2, which is this one. And the internal energy at the beginning is, from the table again, 2506 kilojoules per kilogram. So at the end of stirring, the second pressure is 138 bar. This is given to you. Because of the addition of energy, remember that in systems or in any system, the difference of, or in any system, the difference of incoming minus outgoing energies is going to cause a difference of system energy. For a closed system, the net energy incoming and outgoing is the net Q minus net work, and the system kinetic system energy is the summation of internal energy plus kinetic energy plus potential energy. We have this minus sign because of the sign convention. Remember that if the system does work on the surrounding, it's a plus work. If the surrounding does work on the system, it's a minus work. In this case, the surrounding does work on the system. The gas is being stirred, so it's going to be taken as minus. Minus and minus will make it a plus, which means energy is added into the system. So if you write the energy equation in this form, you will see that the right-hand side of the equation is this part. The change in the kinetic and potential energies can be taken to be zero. The tank is well insulated. It's given in the problem statement. And we have the change in the internal energy being equal to minus W. So W is minus U2 minus U1. First of all, you need to calculate the mass inside the tank. So the mass inside the tank is 0.17 kilograms, so that the work, which is equal to change in the internal energy, is U2 minus U1 with a minus sign on it. So you get a work of minus 33 kilojoules. It means that it's minus because the surrounding does work on the system. That's why you have a minus sign. Another example is regarding a piston cylinder system again, but this time we have three processes. In the first process, we have a constant pressure of 10 bar, and at a constant pressure, the piston is cooled down from 400 Celsius to 180 Celsius, which is the saturation. So the first process is to cool down a 400 Celsius superheated vapor to saturated vapor. you can find the temperature of the saturated vapor at 10 bars from the table. So it doesn't have to be given to you. This 180 doesn't have to be given to you. You can find it from the table. Then, as a second process, it's cooled down to 150 Celsius in constant pressure. So first, it's compressed. It compressed from this volume to that volume. Meanwhile, the temperature drops from 400 to somewhat lower temperature. Then, under constant volume, it's cooled down from 180 Celsius to 150 Celsius. It's asking to sketch both TV and PV diagrams, so we need to draw this. The overall process work, so the work done during the processes 1 to 2 and 2 to 3. Also, the overall heat transfer during the processes. So heat transfer during the process 1 to 2 and 2 to 3. We have two separate processes from 1 to 2, which is under constant pressure, then 2 to 3, which is under constant volume. But if the volume is constant, the work term is 0. So during the second process, there is no work because the volume is constant. So the whole work is because of the cooling or compression from 1 to 3, 1 to 2. So the work per unit mass is, because the pressure is constant during the compression, it says that the pressure is constant, then it goes out of the integral. So the work during the process 1 to 2 is PV, P times V2 minus V1. So you can see that the work here per unit kilogram is minus because the substance, the system is compressed, or in other words, the surrounding does work on the system. That's why you have minus sign. You can write then the energy equation, exactly this equation. So you write this energy equation, Q minus W is equal to d delta U plus delta kinetic energy plus delta potential energy. And by making the necessary simplifications, you can cancel the kinetic and potential energy terms. Then you are left with the delta kinetic energy, delta internal energy being equal to Q minus W. So the heat transfer is the change in the internal energy plus the work per unit mass. First of all, of course, you have to find out the properties in mixture, because during the second process of 2 to 3, the substance inside becomes a mixture. So we have to use the mixture property calculations. In order to use the mixture property calculations, we have to calculate first the quality. The quality of the substance inside is almost 50%. So by using this quality of 50%, we can calculate the internal energy of the mixture. The internal energy of the mixture has always the same kind of calculation. The liquid internal energy plus the quality times the difference of the gas internal energy minus liquid internal energy. So we find the internal energy at the end of the second process to be 1584. So if we put everything in this equation, we will see that the Q during the two processes is minus 1485. It means that in order to get these defined results, this much heat must be lost. So it's necessary to cool the system in order to get the results defined here. Because normally, if you don't cool this, during the compression, the temperature may increase. So the reason why we have a decrease in temperature here is because there is a loss of heat, or there is a cooling process here that causes the temperature to drop from 400 to 180. And this amount of heat removed from the system is given here as minus 1485, and minus Q means that there is a heat loss instead of heat gain. Remember the rule: if W is negative, W is inside the system, so the surrounding does work on the system. If the system does work on the surroundings, it's a positive Q, positive work. But this is opposite for the case of Q. So if the system is losing Q, it's negative Q. If the system is gaining Q, it's positive Q. So what we have here is a loss of heat because it's negative. So after using the property tables, now we can mention other properties such as specific heat. Specific heat is the heat necessary to increase the temperature of a substance by 1 Celsius. So as a definition, specific heat is the heat necessary to increase a substance temperature by 1 Celsius if the substance has a mass of 1 kilogram. As a general definition, there are two kinds of specific heats. One of them is constant volume specific heat, and the other is constant temperature pressure specific heat. The constant volume specific heat is obtained from the partial differential or partial derivative of internal energy with respect to temperature, and the subscript here V means that it's under constant temperature, constant volume, and constant pressure specific heat is obtained from the derivative of enthalpy with respect to temperature again, but it's at constant pressure. So we have two types of specific heat. One of them is CV, the constant pressure volume specific heat, and the other is CP, constant pressure specific heat. And we have another definition, specific heat ratio, which is CP over CV. In the calculations, we will be using both CV and CP as specific heats, as well as the ratio of them. So up to now, we have learned how to find out the properties in mixing zone, in saturated line, and also in superheated region. How about the properties in compressed liquid? You either have to have a table for compressed liquid, or there is another way to find out the values for liquid. You can use the approximation that the property in the liquid zone is approximately equal to the property of the liquid, the saturated liquid, at the given pressure. For instance, you would like to find out the specific volume in the liquid zone. So this part belongs to liquid zone because this solid line is the saturation curve, so that the left of it is subcooled liquid. You would like to find out the specific volume of the liquid at this given temperature, and you can say that the specific volume of the liquid here is approximately equal to the specific volume at the saturation at given temperature. So as a result, we can say that the specific volume at a given temperature and pressure is approximately equal to specific volume at the given temperature. And similarly, you can do the same thing for internal energy. For enthalpy, we need to use something additionally. So the enthalpy at the in this liquid zone is equal to the enthalpy of the saturated liquid given at the given temperature plus this term. However, this term is usually very small, so you can still say that the enthalpy of the enthalpy of the liquid, the subcooled liquid, is almost equal to the enthalpy of the saturated liquid at the given temperature. Remember that enthalpy is a combination property, combination of internal energy plus flow work. If a material is incompressible, meaning that under pressure its volume does not change or its density does not change, then we call the substance as incompressible. Then we have only one type of specific heat, which is C. So for the case of incompressible substances, we have only one specific heat. The specific heats can vary with the temperature. So in order to find out the internal energy change during the temperature change, we may have to use an integral relationship because the CV or the Cp can be a function of temperature. In this case, we have to know the functional dependence of the specific heat on temperature so that we can perform this integral. This is for incompressible fluids. When it's incompressible, we get an ordinary derivative, not partial derivative. So when it's ordinary derivative, you can directly integrate it, because if it's partial derivative, you cannot directly integrate it. So for incompressible fluids, you can integrate the CVdT to get the variation of internal energy. Similarly, you can obtain the variation of enthalpy by integrating this amount. So integration of U plus PV will give you this. Of course, you have to have the functional dependence of C on temperature. So if C is taken to be constant or average, if you take an average specific heat, you have an average specific heat given between the temperatures of T1 and T2, you can always use it as C times T2 minus T1. So in this case, you have a constant average C, or you can calculate the enthalpy by using the average C again. Also, you may need to use the effect of this pressure change. However, most of the time, this pressure term, this term with pressure may be very small because the incompressible liquids, such as liquid water, will have a very small specific volume, so that this term almost vanishes, and at the end you have the enthalpy change for a substance with a constant C and incompressible substance. Okay, do you have any questions before having a break of 10 minutes? So let's have another break, then we will be here at 3 o'clock, 3 p.m. Recording has started. So for ideal gas, we know that the relationship between pressure, specific volume, and temperature can be written as PV is equal to R times temperature. And this is given in terms of specific volume per unit mass, and the R is the gas constant for this given gas. On the other hand, the same ideal gas law can be written as P times V bar, I will explain why bar is equal to R tilde times T. So in this case, this is volume per mole, and this one is the universal gas constant, which is constant for all the gases. So it has a value of 8.314 kilojoules per kilomole per Kelvin, whereas the R here is dependent upon the gas and is calculated from the universal gas constant divided by the molar mass of the gas. So again, if you use the molar ideal gas law, molar ideal gas equation, then you can write it as P times volume per mole of the gas is equal to universal gas constant, which is constant, 8.314 kilojoules per kilomole per Kelvin, times the temperature in Kelvin. Otherwise, you have to use the normal specific volume as cubical meter per kilogram. Then in this case, the gas constant must be calculated from the universal one divided by the molar mass of the gas. So it was shown that this universal gas constant is actually a constant value for all the gases, and according to this graph, you have PV bar divided by temperature, and at the x-axis you have P. So for different temperatures, they all converge at the same value, which is the universal gas constant, R tilde. This is an example of three different processes inside a system where an ideal gas is used. In the first process, the ideal gas is compressed in constant volume from 1 bar to 2 bars. So you can see that the first process is constant volume. So this is constant volume. Then the second process is from 2 to 3, and it says that this process is performed under constant temperature. And the third process is from 3 to 1, and as you can see, the third process is done under constant pressure. So we have three different situations where three different processes are done. The first one is constant volume, the second one is constant temperature, and the third one is constant pressure. Then during the processes, at the end of the processes, we need to find the temperatures as well as the specific volume in state 3. We have a ideal gas, so we will be using either this one or the one with the mole numbers. So the one with the mole numbers has a different volume. So either one can be used. In this case, R tilde is constant, as I say, and V bar is the volume of the per mole. And in the top one, V is the specific volume as cubical meter per kilogram, and VR is the gas constant of the given gas, and it's obtained from the R tilde divided by the molar mass of the gas. So the gas has a constant mass of 0.453 kilograms. Initial temperature is 300. We can use the ideal gas law to find the specific volume of the gas. So the specific volume of the gas is constant because the first process is done under constant volume. So it means that V2 is equal to V1, the specific volumes are constant, so that RT1 divided by P1 is equal to RT2 divided by P2. R's cancel, of course, then we have T2 to be P2 over P1 times T1. Then we see that the temperature at the end of the process is 600 Kelvin. Initially, it was 300 Kelvin. So when the process is done under constant volume, we see that at the end of the process, the temperature becomes 600, from 300 to 600. How about the second process? The second process is constant temperature, so that the temperature of the 3 is equal to temperature of the 1 and 2, which is 600, the temperature that we have just found. Then, by using the definition of universal gas constant and finding the gas constant, the universal gas constant is always something constant. So the gas constant is the universal divided by molar mass of the air. The molar mass of the air is 28.97 kilograms per kilogram mole of air, so that the R value for the air is 287 joules per kilogram per Kelvin. So we can calculate the specific volume at the end of the second process to be RT3 divided by P3, which is 1.7. If you take a look at the graph, that there's an expansion from V1 to V2, and this expansion can also be found from here. If you calculate the V2 and V1, you will see that the specific volume is much less than this, which is also clear from the graph. Okay, these are the relationships between the specific heat and enthalpies and internal energies. Remember that for an ideal gas, we can always write that the constant volume specific heat is obtained from du over dt, the derivative of internal energy with respect to temperature at constant volume. And therefore, the internal energy change can be calculated from the integral of Cv dt, but in this case, we have to have the functional relationship of specific heat of this gas that varies with the temperature. Similarly, we can write the constant pressure specific heat as dH over dt, then integrating it over temperature, we obtain the enthalpy change, similar to the internal energy change, as the integral of Cp dt, but also the functional relationship Cp with the temperature must be known in order to perform this integral. By the definition of enthalpy, it's a combination property, as I said, it's U plus RT, so that enthalpy and internal energy can be related to each other, so that the specific heats are related to each other also. It's important to see that the constant pressure specific heat is equal to Cv plus R, or you can also use it for molar basis. This is mass base. This is the molar base. When you have a bar on top of something, you need to understand that it's molar basis. So you have mass basis relationship between the specific heat and molar basis relationship between the specific heats. Also, again, by definition, the ratio of the specific heats is Cv over Cp, and by using this, you can write Cp as K times R divided by K minus 1, and Cv R divided by K minus 1. Because specific heats are mostly a function of temperatures, then we have to know the relationship between the variation of the specific heat and temperature, so that we can calculate the integrals and find the values of the changes in internal energy and enthalpies. As an example, some gases, for instance, carbon dioxide, water vapor, oxygen, carbon monoxide, hydrogen, their specific heats varies with temperature in an increasing tendency. But in monoatomic gases, the noble gases, these are the noble gases, monoatomic gases, the specific heats do not change with temperature, they're constant. Actually, if you look at the y-axis, you will see that it's Cp over R. And this Cp over R is constant for noble gases at a value of 2.5. So for a noble gas, for a monoatomic gas, the Cp divided by R is always constant, but for other gases, they change with the temperature. So what is the way to find the integral if you don't know the value of the variation of specific heat with temperature? In order to find the integral value, we can directly use some tables, because there are tables like air table. I have provided the air table to you. You can just read the enthalpy values from this table and find out the difference in enthalpy or internal energy. So all you have to do is to use the table, and using the temperatures, you can find either internal energies or enthalpies to find the values of the internal energy and enthalpy and find the differences of them. Okay, these are some values of examples of enthalpies of air, because normally enthalpy is related to Cp and temperature, but this relation is not given anywhere else. However, by using this table, you can find the enthalpy change in a gas if the temperature has changed from, let's say, 200 to 290. So the enthalpy change is found from the enthalpy in 290 minus 199.97. So the enthalpy change during the temperature change from 200 to 290 is enthalpy change given here. You can also find the internal energy change from, let's say, 200 to 206. An example of using the gas tables. So we have a piston cylinder system shown here. In the piston cylinder system, there is an air of 0.9 kilograms. Initially, it was at 300 Kelvin, and it's compressed to 6 atmospheres, so that the final temperature becomes 467. So initially it was at 1 atmosphere. At the final state, it becomes 6 atmosphere because it's compressed, and the initial temperature was 300 Kelvin, and also initial internal energy, according to the problem, is given as 214 because it's found from the table, and final temperature is 467, so that the final internal energy found from the table is 337. It also says that during this process, the cylinder is losing some heat of 21 kilojoules. Minus sign means that there is a loss of heat energy, so that when you write the conservation of energy, Q minus W is equal to delta U, only because we assume that there is no change in kinetic and potential energies. And work done, therefore, is found from Q minus delta U, and Q is given, is the heat loss, minus the change in the internal energy. They are the values found from the table. And we see that the work during the compression is minus 130. And as you can see, because of the heat loss, more work has to be done in order to compensate for the heat loss. So during the compression process, there is also a heat loss, and this heat loss is adding to the total energy during the compression of the piston inside the cylinder. So this first part is due to the heat loss, and this second part is due to the change in the internal energy because of the compression. Another example is related to mixing of two gases. There are two tanks of carbon monoxide, and these carbon monoxide gases are mixed by opening the valve in between. In the beginning, before the valve was opened, the first tank had 2 kilograms of carbon monoxide at 77 Celsius and 0.7 bar, and the second tank has again carbon monoxide but 8 kilograms at 27 Celsius and 1.2 bars. When the valve is open, of course, the final pressures and temperatures and everything will be the same, but we have to find the equilibrium conditions after the mixture has finalized. So at any instant, we can calculate the properties of the gas because carbon monoxide is also another ideal gas. So we will be using always the PV MRT equation. Sometimes you can see the equation as this one. PV is equal to MRT. Or if you divide each side by M, you can also see it as small case v RT. They are the same equations. This is the normal volume, cubical meter, and this is the specific volume, cubical meter per kilogram. So once the mixture has reached equilibrium, so when the mixing has finalized, we can say that the final pressure times the final volume must be equal to final mass times R times final temperature. So this ideal gas equation is valid for any instant. We have the masses in the first tank, in the second tank. Also, here at the denominator we have volumes, so that volume can be written in terms of mass, temperature, and pressure. So this one is volume, this one is volume 2. And we can calculate the final pressure after the mixing to be 105 bars. In order to rationalize the result, we can compare it with the initial pressures. The initial pressure in the first tank was 0.7 bar. The second was 1.2 bar. We cannot say the final pressure is going to be exactly the average of them, but it should be something in between. So if you check the average pressure is almost 1 bar, and according to the calculation, the final pressure 1.05 bar, which seems to be reasonable. So after the mixing or during the mixing, we can write also the energy equation as du being equal to Q minus W. We don't have any change in potential or kinetic energies. Here, there is no moving piston, only a fluid moves from one tank to another so that there is no work done. This is important. So when there is no change in volume, as you can see, the volume does not change. The total volume is the same. So we should say that the work is done here is zero. So it means that during this mixing, the heat exchange between the two mixing is U final minus U initial. So U initial can be found from the total initial internal energy of two separate tanks. In the first tank, we have M1 times UT1. In the second tank, we have M2 times UT2. In the final situation, we have M1 plus M2 times UT final. So Q is the difference in the final and initial situation. And if you write the equation in terms of specific heats by assuming that the specific heat is constant, then the Q is M1 CV times T1 minus T final minus T1 plus M2 CV times T final minus T2. So if you insert the numbers, you will find that there is a heat transaction of plus 37 plus 25 kilojoules. It means that there is a heat transfer into the system because it is a plus sign. There are many types of processes, such as we saw in the example. It could be constant volume, it could be constant pressure, it could be constant temperature, and the process can also be something called polytropic. If a process is polytropic, then PV to the nth power is constant. N can be any number between minus infinity to plus infinity. And when we have PV to the n to be constant, we actually mean that P1 V1 to the n is equal to P2 V2 to the n, or in other words, the ratio of the pressures is equal to ratio of the inverse of the volumes to the nth power. When we have a polytropic process, then during this polytropic process, it can be compression or expansion. The work done is obtained from the integral PV. So if you use the variation of PV, P as a function of volume, meaning that if you write the pressure, for instance, as constant divided by volume to the nth power, and if you integrate this, you get the work for the polytropic process, and this is valid for n is different from 1, because when n is 1, then you have 0 at the denominator, which makes it mathematically indefinite. So apart from except for the value of n being 1, this is the work done during the polytropic process. If n is 1, the work done becomes as this one. So these are the two limiting cases. We have n equals 1, and n is different from 1, in which you will be using the calculation of work by using this, or for the case of n equal 1, you get this. So when n equals 1, it means that PV is constant. When PV is constant, when n equals 1, PV is constant. So this is when n equals 1. And it actually means that temperature is constant, because PV is RT. If PV is constant, R is constant, so T must be constant. So this is when the temperature is constant. An example regarding this, there is a piston cylinder system in which the piston is moved to the left so that the gas inside the cylinder is compressed. And this is a polytropic process, and the constant of polytropic process is 1.5. So it's given you as n is equal to 1.5. So the compression takes place polytropically. This is the work calculation equation that you will be using for the case when n is different from 1. So initially, the gas inside the cylinder was 21 Celsius, and the table value of the internal energy is 210, and initial pressure was 1 atmosphere. The final pressure is given as 5 atmosphere. So by using the polytropic process, you can calculate the temperature at the end of the compression. So the temperature at the end of the compression is from the previous chapter. You need to go and look at the previous chapter. In the previous chapter, the relationship between the temperature and the pressure is given as this one. So here in this chapter, the relationship between the pressure and volume is given, and also the relationship between the pressure and temperature in the case of polytropic process is given as this. So the final temperature is found to be 427 Kelvin. So with 427 Kelvin, you go to the air table and find the internal energy value to be 306.5 kilojoules. And from here, you can write the energy conservation equation. According to energy conservation equation, Q is W plus delta U, or per unit mass. Q divided by is equal to W divided by M plus the difference of the internal energies per unit mass is found to be minus 13, or in SI units, minus 30.5 kilojoules. It means that in order to realize this process, there is also a heat loss. So even though the pressure and the temperature seems to be increasing, at the end of the process, we also see that there is an increase of the temperature of, there is a loss of heat of minus 30.5 kilojoules. So we always use the same kind of approaches, which are delta energy, the change of the system energy, is always equal to net Q in and out of the system minus net W in and out of the system. So this is always the starting point for a closed system. For the case of an open system, which we will see next week, we will include something more, but let me not mention it here. For a closed system, this is always the starting point, and it's actually the conservation of energy, because the net energy change within the system is equal to energy transferred to the system in terms of heat or in terms of work. So the energy transfer to and from a closed system is only either in terms of heat energy or work energy. Do you have any questions? There are many new concepts, so sometimes you may find the solutions complicated, but you have to go back to the principles and concepts. Otherwise, thermodynamics may be difficult. However, on the other hand, if you learn the concepts and the use of the uh, tables and charts, then you will find that the solutions are not so difficult. So any questions? Okay, it looks like you don't have any questions. So I can stop here for this week. So I wish you a nice weekend and see you next week. Bye.